All right. Good morning, everybody. Today, Tiger Genusi is the speaker. He will be presenting his view on photonic integrated circuits. So, Tigers, please, we look forward to hear your talk. Yeah.
Thank you very much for the introduction and for having me here. So, I'm sorry that the title is not appearing, but in the slide, I promise you can see it. So the idea of this presentation is to discuss about assembly and packaging challenges for the commercialization of photonic integrated circuit for neuromorphic computing. So the outline will be an introduction on what's the purpose of the techniques of designing PCBs and the fiber array attachment and all the challenges for the assembly. Then go more in deep with the electrical PCB and breakout board that we designed specifically for our neuromorphic computing PIC and the main challenges that we have when we want to do the fiber array attachment or assembly. So the idea is that we have the photonic integrated circuit chip for neuromorphic computing, and here we report the image of the fabricated chip, actually already at the final stage of the assembly, but we want to highlight which are the main challenges. So as you can see, during the assembly stage, we have electrical ports, well, input, output optical ports, and also input, output electrical ports or connection that are used to control both actuators and electrical monitor, such as, for example, power monitors. The location of these ports is carefully chosen, and especially what we do is that we try to put on opposite sides the electrical ports and the optical ports. In this circuit, I just want to mention, because maybe it could be misunderstood, there are two different circuits, but later on we will see it. And actually, since the optical ports are opposite and also the electrical connection, we can notice that only one of the circuit can be packaged at the same time. So typically, there is a big question of what is assembly and what is packaging. So I would just want to give a brief explanation on this. So assembly is the process that combines individual components of the photonic system into a single functional unit, while packaging is the enclosing of the assembled photonic circuit into a protective housing or enclosure. And given this general definition, if we look at the sub-tasks that we have to do, they are typically very similar, but the essential difference is regarding from a detailed individual components to a already assembled photonic engine. And in this presentation, actually, what we are going to discuss more in deep is assembly, and we are going to discuss component alignment. So how we align the optical component, how the precision that we have at the level of submicron precision in order to ensure optimal light coupling between the PIC and the external devices, for example, a fiber array. The die bonding, so then we have to mount the photonic chip into a substrate or what we call as a carrier, and we have to use an adhesive in order to attach the chip. Uh, in some cases, the chips can be somehow soldered in order to there is also a soldering process in order to secure mechanically and terminal stability. Then there are also the electrical connection. So we have to establish secure and stable electrical connection between the photonic integrated circuit and the external electronics. And this typically can be done with wire bonding, flip chip bonding, or other advanced technique. it will not be the purpose of the presentation, but I will explain a bit which kind of connection we have and which design we have done in order to secure the operation of the PIC. And then the thermal management. It is important to implement some thermal control system to prevent the PIC from overheating, and we will show how we do this with the use of a peltier. Uh, Sorry. So this is the typical, let's say, the 3D view of our assembly. And then also, if we want to go to a next stage to the packaging, where we have the PIC that is located here. We have the PCB, which is this green part. Uh, Typically, we have a metal base, and then we have the heat sink base. And so there is the first layer of the metal base, then there is where we locate also the peltier. Then there is a heat sink which will conduct the thermal dissipation very fast from the peak to the heat sink. We typically have a protective metacrylate. Then there is the optical epoxy, which is the adhesive that attach, let's say, the fiber array towards the heat sink or this layer here. We have a fiber holder, so there is a specific uh, placement for the fiber. And then we have let's say, the fiber array and a specific design for, let's say, the position where the fibers will be located, and a structural epoxy in order to make this place fixed and not move. So regarding our design, this is the layout disclosure that we have to uh, give to the electronic designer, which has to design the PCB. So what we have to highlight is the location of the input optical ports. For example, here there is circuit 1 and circuit 2. And as you can see, for circuit 1, these are the electrical connections, while for circuit 2, we have the electrical connection on the opposite side. As I said before, in this specific design, we have two different circuits, but at the stage of the assembly, we will assemble only one circuit per time. We highlight which are typically the grounds and the signals, because it is very important for our circuit to understand, for our PCB design to understand which are the signals, because here we have to put actually the real, let's say, electrical connection, while the grounds actually can be paired in multiple grounds depending on the circuit. So let's go a bit more in detail with the PCB and breakout board. Uh, let's see a bit on the assembly description. So it is important to understand also how this will be assembled in one single piece, and our mechanical designer uh, will try to define all the screws that can be used in order to mount this assemble in a holder where this can be then used and easily, let's say, placed during the different steps of the process that I will show later on. Because since we will have fiber array mounting, for example, wire bonding, all these steps are done at different stages, and so the chip has to be secured with the specific screws that can be used at different steps during the process. Then we go for the PCB design. Um, it was the PCB design was not part of essentially the core of my activity during the PhD, but it is important to have a very clear communication with the electronic designer in order to guarantee that the connection of the PCB are the same of the connection that we want to have inside the circuit. Specifically, I will not enter in the detail of the specification of the PCB design, but what is important to define typically is the width of the track, the pitch, and the gap between different electrical components. Then we have this is the PCB design that takes the connection of the circuit of the PIC that will be located here into a connector. Then this connector will be placed on a breakout board. Since we have two circuits, we actually require two different, let's say, breakout of the connection from the circuits to, let's say, the um, uh, current controller or voltage controller that we will use in order to control the circuit. Let's go a bit more in detail. Since we have why there is the need of this interposer, and we cannot have one single connector that connects to our electrical source provider. The reason is because first of all we have two different circuits, but more in detail is because inside our circuits the signal and ground connections are mixed. What does it mean? It means that for different signal actuator, we have, in order to fit inside the design area, we have collected multiple grounds. This technique that is typically used at the design stage where the design area is small is not good in order to use a general PCB because uh, the ground and the signal is required to be specified in the schematic, and so then when we apply the electrical connection. So big designer suggestion in general is that if it is possible and if there is enough space in the design area, do not group the signal grounds in order to use a very general connections in the PCB. And this in general will reduce the cost and the PCB difficulty. Later on, once the design is done, the PCB designer will provide all the connector and identification of the connection that we have inside our circuit in order for us to be able to connect to our source current or voltage source and apply the bias condition that we want to have in order to use our actuator or collect the light in our power monitor that we have. And so it is important to define which are the pins, for example, for the electrical connection or for the thermistor, and the ones that obviously are not used. Here I want to just highlight which is the assembly process. So the first task that we do is the PCB preparation. So the electrical connector and thermistor has been soldered to the PCB because any mechanical stress can then um, have an implication on the wire bonding, for example, or the fiber attachment. So we pass from a more general view to a more detailed view. So the PCB preparation, then we have the PCB attachment to the PIC chuck. So we connect the PCB, both sides, with epoxy and screws to the PIC chuck. Then we have the PIC attachments. So once we are sure that the PCB does not move, we need to attach the PIC to the PIC pedestal, and this is done by visual recognition of both the PIC and the pedestal. Once the PIC chuck has been used to ensure that the chip is aligned and centered into the assembly construction. Ensuring that the PIC is attached, we can now do the wire bonding between the PIC and the PCB that is already attached. So we assure that all the electrical ports are stable and wire bonded to the chip. Then a visual inspection is done in order to ensure all the connections are done properly. Once the electrical connections that are relatively more stable from mechanical stress than the fiber attachment itself, we can proceed with the fiber array optical alignment. So typically inside the design, we use some what is called U-loops. So the U-loops are connections that enters, for example, from on port 1 and exit in port 2. And also in this case, we have the same for 7 and 8 in order to inject light in port 1 and extract light in port 2 and see if the fiber array is correctly aligned. If this is done for the lateral port, these lateral ports and the internal ports are between 2 and 7, this guarantees that also the inner ports are aligned. Once the active alignment is done and maximized, we proceed with the fiber array attachment. And we will describe this in the following slides. So one of actually the main challenges is the fiber array assembly. Let's understand a bit why this is a challenge. In general, for a photonic peak designer, there are essentially two general way to couple optical structure into with a fiber array. And this in general called as both size converter. What does it mean, both size converter? That we need to convert the spot of the mode field diameter of the waveguide optical light to the spot or mode field of the fiber array. And the most easy building block that can be used is the what is so-called inverted taper. The inverted taper function is to adiabatically change the optical mode to the optical mode of the fiber. So we do this shrinking or tapering of the waveguide in order to make the optical mode bigger and adapt to the one of the fiber array. A more sophisticated design is the so-called suspended waveguide and edge couplers. So what we typically do here is that the confinement of the mode is in between air and silicon dioxide of the cladding. This is done in order to match the mode field diameter of the glass fiber. Why there is this difference? Because typically the integrated photonic waveguide is, for example, used with silicon on insulator or silicon nitride on insulator. So the material is different from the material of the fiber, and so the optical mode is smaller. But if we, for example, use the silicon dioxide, which is a glass confined with air, this is much more similar to the optical fiber, and so the optical mode here it's much more similar to the optical mode of the fiber array. Uh, in general, there are different techniques for the assembly of the fiber array. The most common one and that is typically used is the direct attachment. So we have the fiber array here and the PIC here. The structural epoxy that we showed before, where we attach the fibers to the let's say the fiber pedestal, and the epoxy is located in between the PIC and the fiber array. So the epoxy, just to mention it again, is the adhesive. So that we attach the PIC and the fiber array. But which are the problem? The problem are that during the direct attachment, the fiber array is attached directly to the pedestal instead of the edge of the photonic integrated circuit. So there is first of all here an attachment. So this attachment here is not very stable because the most of the weight is on the fiber array. And when then we attach also the epoxy here and the adhesive here, there can be a shrinking during the process that can make the alignment very, very difficult. So the next stage that we want to do is an indirect attachment. So where the shrinking does not interact with the PIC, but interacts only with the height and the position of the fiber array. Which are the process steps that we need to have when we want to attach let's say the fiber array and the chip. Well, first of all, the chip. But this process is very similar also when we want to position let's say the fiber array. Oh, sorry, 1 second. We have that for the chip attachment, we have first of all an initial preparation where we have to create a specific recipe in order to assure that the adhesive is the correct one, and we characterize the specification of the adhesive. Then we assemble during this we have to define, for example, the curing time and the shrinking properties of the epoxy. We have the assembly. We have to measure all the feature of, for example, the chip pedestal or the fiber pedestal. We have to pick up the chip, but also, for example, this is the same. We have to pick up the fiber array. We need to apply the correct rotation in order to be aligned with the chip. And then there is the part of the chip deposition or fiber array deposition and the fixation. This is process, I explained it here for the chip, but it's the same also for the fiber. Sorry. Now we want to pass for an indirect fiber array attachment. So the idea behind that I explained before behind this indirect attachment is that we want to attach the fiber array to the PIC chuck and not anymore to the PIC. So we want to attach to the fiber array, for example, here pedestal or PIC chuck. So we leave a specific gap in between the PIC and the fiber array. This approach has the advantage of not leaving residues of the epoxy on the PIC when we have the attachment. And so the shrinking does not affect the distance between the fiber array attachment and the PIC. But apart from that, during the shrinking, part of the epoxy can go over the chip. And if we have, for example, a device that has a suspended edge coupler, the epoxy can enter in the air gap that we have in the chip, and so can induce some mechanical stress on the suspended waveguides. So the process development consists on calculating uh, uh, the current amount of epoxy to locate and calculate also with the curing process and the factor of shrinking the height that we need to locate the fiber array in order that after the curing process the fiber array is aligned with the peak. With our calculation, specifically, we understood that we need to locate the fiber array at 1.5 micrometer above the peak. Then, as I said, we have which are the process steps that we use to do this. We have the chip identification. So we have a visualization of where the chip is. We have the fiber array grip that is specifically designed for uh, um, taking and the fiber array. We have to apply the specific rotation to the fiber in order to position it perpendicular to the chip. We have to apply specifically also movement to the fiber array in order to guarantee an initial alignment. We do an area scanning, so we move the fiber array in different direction Y and Z. Well, this is the system of coordinate that we use in our visual inspection tool, and we recreate a wafer map that tell us which is the correct position where we collect most of the power from the fiber array and the alignment loop. Once the area scanning is done, we move to a safe position. We apply the correct adhesive, and then we move again to the optimal position. All these steps, for example, are monitored continuously, and here you can see the evolution in time of the alignment. And once the adhesive is cured, uh, uh, we uh, we we have this application to the tail of the pedestal, and then we have also the tail adhesive curing in order to fix this part of the fiber array that is floating. This is very important because, and actually this fiber tail adhesive curing is done here, is very important because when the grip is released, there will be a big stress that will be applied on the fiber array, and if there is no enough adhesive force applied, this can cause the detachment of the fiber array. And then we have the fiber array release. Here we report the fiber array results where we have the different trials that we have with the different peak and with the monitor the different loop. So we provide the source and the dry alignment, and we want to understand which is let's say the losses that we have after the curing. And so we have to consider a few things. So during the initial fiber attachment, sometimes we can have a collision if we don't monitor correctly the distance between the fiber array attachment and the chip, and this can damage substantially the suspended couplers and can reduce a lot the power that we have, and this can be seen, for example, for this peak. So we calibrated more carefully the distance and the visual inspection tool that we have in order to characterize this distance. And so for the next stage, we don't have this kind of problem. And actually the dry alignment and after curing are much more similar. But the second problem that we have is why we have lower power in the dry alignment of the source of the loop 7/8, which is this one. This is due to the fact that there is an overhang of the chip in this side. Typically, this is not present, but for this kind of chip, there was this residue, and one of the things that can be done to remove this is a polishing, but we didn't want to risk to induce mechanical stress of the suspended waveguide here. And so we assume this problem and we proceed to the alignment taking care of this problem. And as we can see, there is a drop in the alignment. But for next design, for example, the solution is to locate the suspended coupler towards more of the center of the chip in order to avoid this overhanging. And here now we have the final assembly where we have the different metal plates, the methacrylate over it, the Peltier placed under the chip, and all the metal threads are provided in order to take this assembly and mount on a external mechanical stage. The fiber attachment is done and secure, and then there are all the optical connector of the fiber array. So in conclusion, just a few suggestions that we have is take in consideration the carefully electrical connection inside the chip in order to easier the design of the PCB. We have developed a new way to attach the fiber array into the chip by indirect fiber attachment, which guarantee an easier process when this is calibrated and does not affect the chip during the attachment process. Thank you very much for your attention. If you have any question, please.
Yeah. So I will stop the recording now so we can have the questions. So